Good morning. I'm Hyeontaek from Carnegie Mellon. So I'm going to present MICA, a holistic approach to fast in-memory key value storage. This is joint work with Dongsu of KAIST, David Andersen of Carnegie Mellon, and Michael Kaminsky of Intel Labs. So the goal here is to build a very, very fast in-memory key value store. So we want to improve per node performance measured in operations per second per node. By having very fast node, we can build very less expensive cluster of key value stores by using a fewer number of nodes. Also, we can mitigate the hotspots much more easily because individual nodes are more powerful. We can also reduce latency for applications using multiple queue queries because they do not need to interact with many nodes in the cluster, and they can expect a lower latency variance. Our specific target here is to support small key value items whose request and response fit in a single packet. So this captures many interesting and important applications of in-memory key value stores. So we do not provide a new cluster architecture, but we expect to use the same or similar cluster architectures as before. And as in ManCached, we do not provide the durability. So let me begin by comparing the current system's performance. So we use YSSB, which is the de facto standard benchmark for key value stores. And we focused on in-memory storage. So we turned off logging in our own experiment. We measure end-to-end performance over the network using a single server node. So this plot will show the performance comparison. So we are comparing 4 different systems here. So open source ManCached, and Cloud in SSB 2011, and MEMC3 from last year's NSDI, and MES3 of EuroSys 2012. So the y-axis is throughput in million operations per second, so higher is better. So I'm going to use 3 different results here. So the first result is using read-intensive workload. So this is a published result from the publication, and because we cannot control the evaluation setup, the systems will use different configurations and different hardware. The second result is from us. We ran their system on our test bed, and we used the read-intensive workload, but we optimized their systems by applying IntelliDBTK, which bypasses the kernel to achieve low overhead I/O. Also, we turned off the logging. In the third result, we used a slightly different workload that has lots of write. So only 50% of operations are get, and 50% of operations are put, which is write. So from the published result, we can have some basic idea about system's performance, even though this uses different system configurations. When we optimized their systems using our fast packet I/O, actually we see improvement for most of the systems. So now the fastest one, MES3, can achieve 16.5 million operations per second. But surprisingly, when we use write-intensive workload, the performance collapses. So now many systems achieves only 1 million operations per second, and MES3 is achieving only 6.5 million operations per second. So how does that compare to our system? So in our system called MICA, you achieve 65 to 70 million operations per second using the same hardware in a single server. This is 4 times to 13.5 times higher throughput than the second best system. And MICA's throughput is close to the maximum packets per second we can achieve on this server. So how do you achieve such a high performance using MICA? So in MICA, we redesign in-memory key value storage by applying a new software architecture and data structures to the general purpose hardware in a holistic way. This diagram shows the abstract view of in-memory key value processing. Client sends a request to the server, and the server NIC receives the request and distributes requests to different CPU cores. And CPUs access the data in memory to handle the query. First, MICA optimizes the parallel data access between CPU cores and the memory. And second, MICA uses better request direction between the client and the server CPU cores using general purpose NICs. Third, MICA uses new key value data structures. Specifically, MICA supports both cache and store modes. So what I mean by the cache mode is that MICA can evict items automatically to reclaim space for new items. And in store mode, MICA does not evict items automatically, but it preserves all stored items. So in the rest of the talk, I'm going to describe the design of these three components and go back to the end-to-end evaluation. Also, due to the time constraint, I'm going to mainly focus on the cache design of the MICA instead of explaining all the details of store design too. So the first part of MICA is parallel data access. The goal here is to exploit the CPU parallelism efficiently, because now server CPU has lots of cores, like 8 cores, 15 cores, and so on. The common parallel data access scheme used by many key value stores is concurrent read, concurrent write. So in this scheme, server CPU cores can access any location of the memory, and sometimes it's done concurrently. So because there's no hotspot in the CPU cores, you can expect good load distribution across all cores. But one downside here is that the CPU scalability is somewhat limited, because when data is accessed concurrently by multiple CPU cores, you need to do some form of synchronization, which requires expensive intercore communication. Also, a CPU core may access remote memory that is not in the same NUMA domain, which incurs extra memory access latency. In MICA, we use exclusive read, exclusive write. We divide the data into smaller partitions, and each partition is accessed by only one CPU core. Because there's no concurrent access, there's no need for synchronization, so we can achieve good CPU scalability. But this may suffer from low performance under skewed workloads, because some CPU cores may be overloaded when the workload is skewed. But MICA does not have a serious problem with the skews, because MICA is more like a memory access intensive system. That's a computationally intensive system. So actually, the previous numbers I have shown was using skewed workloads. So I want to compare the performance between concurrent access and exclusive access. Because even though other systems were using concurrent access, their performance was so low, so we implemented our own version of concurrent access on MICA. So on the left side, you see concurrent access version performance, and on the right side, you see MICA's exclusive access version. So I used 4 different workloads, which is a combination of uniform and skewed workloads, and write-intensive and read-intensive workloads. So one noticeable difference between two groups is that concurrent access version does not perform very well under heavy writes. So the performance is below 50% of exclusive accesses. So exclusive access version provides constantly high throughput regardless of the skewness or write intensiveness of the workload. So it's a safe choice to use. In the second part of the MICA, we want to perform better request direction by sending requests to appropriate CPU cores, because it can improve the data access locality by exploiting the cached data in the CPU cache. But in MICA's exclusive access, this is very important, because each request must be sent to a corresponding partitioned core for eventually for request processing. So if we can realize request direction, efficient request direction without using any CPUs, then we can maximize the benefits of exclusive access. The common request direction scheme found in many systems is flow-based affinity. So in this scheme, NIC uses 5 tuple of packets to classify packets and then send them to different CPU cores. So all packets from the same client goes to the same CPU core. This can achieve a good locality for flow-based communication, such as HTTP over TCP, but this is suboptimal for small key value processing, because a single client can request different keys, and all of the requests go to the same CPU core, ignoring any data access locality. in MICA, we use a different scheme, object-based affinity. So in this scheme, we ignore who sent the request, but we only care about what keys are being requested. So as shown in the diagram, all requests for key 1 go to the same CPU, and all requests for the key 2 goes to different, but the same CPU. So this can provide good locality for key access, but one challenge here is that it's difficult to implement using general purpose hardware efficiently. So we could implement this using software as done in prior work, such as CPH and Kronos, but we found that it's much more efficient to use client assist or possibly special hardware to implement this request direction. So let me briefly explain the client assist we are using. So basically, client assist is makes the client to pre-process the request on the client side to extract the classification information, and then put the information as a part of the packet header, in fact, as a UDP destination port number, so that the general purpose NICs can just use the port number and send the package to different CPU cores. So in this plot, I compared the performance between software implementation of object-based affinity and the MICA's object-based affinity. So this is very clear that software-only solutions achieves only 40% of the throughput the MICA's hardware solution can achieve. So it's very crucial to use NIC hardware to achieve efficient request direction. The third part of MICA is new key value data structures because they have a significant impact on key value processing speed. So also we want to have a new design to achieve a high read and write speed. So everybody agrees that fast read speed is good, but why do we care about fast write? It's because we are seeing more and more applications that are write intensive, so they can benefit from fast write, and also fast writes can improve the data ingestion speed and recovery speed. As I mentioned, MICA provides both cache and store modes, and MICA uses different sets of data structures for different modes. For MICA's cache, we use two data structures. So circular log is the memory allocator for key value items, and lossy concurrent hash index is an index to allow fast item access to the data stored in the circular log. These data structures exploit Memcached-like cache semantics. So what I mean by Memcached-like cache semantics is that there's Memcached is a cache, and it can evict items automatically because there's a separate storage, such as database or persistent key value store. They can store items safely. So even if we lose some data in the cache, we can recover the data from the original data source easily. This is not completely free, but as long as we lose the data just as much as Memcached does, then we are just pretty fine. So we can optimize the data structures to lose some data and accelerate the data processing. Also, we want to provide a good memory efficiency because the efficiency leads to the capacity of the system, and we are required to implement automatic item eviction because to follow Memcached semantics. So circular log is a memory allocator for key value items. So this combines a traditional log structure and circular queues. The goal here is to simplify garbage collection and free space defragmentation. So as in similar to traditional log structure, all the items are appended at the end of the log, converted as a sequential write in the memory. But unlike a traditional log structure, we do not extend the log or allocate new log pages when log is full, but we reuse the log space again and again in a circular way. So basically, we evict all this item from at the head of the log to make room for new items. So basically, this realized some 5-4 item eviction, but we can also extend this scheme to support ARU by reinserting recently accessed items at the tail of the log. We need an index to find items very quickly because circular log is simply a memory allocator. So we use a lossy concurrent hash index, which is a set associative in a table, which you can find in CPU caches design. So we have multiple buckets indexed by the hash of the key, and each bucket has multiple entries. So the index entry for this key can occupy any entry of the same bucket. And essentially, the index entry is a pointer to some location in the circular log. So by following the green arrows, you can find the full key value items very quickly. But one thing you can notice here is that there's no hash collision resolution that is found in normal hash table implementation. So but actually, when the bucket is full, then we simply evict the oldest entry from the bucket to accommodate a new index entry. And this allows very fast indexing of new key value items, and that's why MICA achieves so high write speed. So let me briefly mention MICA's store data structures. So in store mode, we cannot evict items, but we have to preserve all stored items. So we cannot use the same data structure, but we use more traditional data structures. So in fact, they use slightly more memory, but we could make them achieve almost as fast as cache data structures. So I'm omitting the details of these data structures, so please refer to our papers for more details. So let's go back to end-to-end evaluation. So I want to show you more throughput and latency characteristics for MICA. So this throughput graph is essentially the same as the first graph I have shown. I already mentioned that there's a large performance gap between MICA and other systems, and MICA does not suffer from some performance penalty of high write ratios. One thing we can notice here is that actually the shape of bars are kind of different. So the reason is that MICA and other systems hit different performance bottlenecks of the system. So MICA is at this rate. PCI Express is the bottleneck for MICA, but other systems are bottlenecked by CPU and memory access. This is the last evaluation slide I'm going to show. So I measured the latency characteristic, and latency is a function of the throughput. So we compared the MICA with the original main cache. So original main cache used the standard socket I/O instead of our optimized network stack. So on the left side, you can see that original main cache does not perform very well in terms of throughput. Also, it requires around 40 microseconds of latency per query. But MICA's latency ranges between 24 microseconds to 52 microseconds. So basically, when we are using the same level of latency of 40 microseconds, MICA is 200 times more faster than the original main cache. So main cache, so MICA provides both good throughput and latency. So to conclude, in MICA, we redesign in-memory key value storage by combining a new software architecture and data structures in a holistic way to address performance bottlenecks in different parts of the systems. So, as a result, MICA achieves consistently high throughput regardless of a heavily skewed workload and write-intensive workloads. So a single MICA server can achieve 65.6 million operations per second. The source code of MICA is now available at GitHub, so if you are interested, please try it and let us know your thought and comment. So thank you for your attention, and I'm willing to take questions.
So a question about the performance coming out of these three different tracks. Like, do you have any numbers on what contributes how much performance?
Yeah, the contribution of different components. So basically, we did not measure how much contribution each component makes, but instead, what we have done is to replace one component with an alternative method and observe how much decrease we see in terms of the throughput. So when we did that, so some of the graphs I have shown in the talk was doing that. So basically, when we use concurrent access instead of exclusive access of MICA, the performance was below 40% of the original performance. And when we use software-only solution of request direction, it was also around 40% of the original MICA's performance.
Okay.
Hi, again, I'm from Voldemort NoSQL database. So nice work. My question is, so I have a concern that because you are comparing to existing industry solutions, and your solution is more like a prototype, not with a lot of management and monitoring, that kind of thing. So I would argue that the comparison in performance is not totally fair because they have overhead for manageability and that such thing. I would argue, say, if you are able to reproduce a prototype like Redis, maybe the performance gain in your design might not be 100x, might only be like 50 or 20x.
Yeah, there might be a possible limitation of our evaluation. So in fact, we would love to use actual application, actual data to evaluate our system and compare systems in a fair way.
Thank you.
Rishi from UCSD. So it's related to the previous question. So you early on you showed that exclusive read performs better than your concurrent read and write performance. So I was wondering if you compared your system with partitioned databases with your kernel bypass mechanism.
So is the question the comparison between some partitioned database?
Partition key value source, for example, running single-threaded memcached on each core, then evaluating your system with the...
Okay, yeah, that's a good question. So we could run single-threaded key-value store in each core and pin each instance to a specific CPU core. So actually, you can reproduce most of the benefits we can obtain using the exclusive access mode if the pinning is well done and request direction is well performed. But one thing is that due to the time limitation, I did not explain the another concurrent access mode, which is concurrent read and exclusive write. In this mode, actually, data is still partitioned, but it could be accessed by multiple CPU cores. And but still, there's only one writer. So such a hybrid mode is only supported by using this MICA architecture, and not by using multiple instances of single-threaded key-value servers. Also, I did mention the benefit of using this concurrent read exclusive write mode, but the thing is that it's the fastest option for read-intensive and skewed workloads.
Ryan Sitzman, Microsoft Research. So I love the circular cache that you have there, but I had one thought on it, one question, which is there's basically two forms of eviction that happen. You can miss in the hash table or you can miss in the log. And if your hash table is too small, then it won't contain enough space to cover all of the objects you have in the cache. And on the other hand, if it's too big, then you're wasting a bunch of space in your hash table. So I was wondering if you had any thoughts on how you kind of dynamically keep track of where the cache misses are coming from, because it's a hash table, because of the buffer was too small to begin with, and whether if there's some kind of interplay there that you can figure out and kind of balance the size of the two things together.
Yep. Yeah, it's a good point. Actually, we do not do any dynamic reconfiguration of the system, and it would be very useful if one part of the memory is insufficient. So basically, but as an alternative solution, we could have used the lossless version of the hash index that is used by MICA store. Then actually there will be no overflow in the hash table, and the only source of the data loss would be the circular log. So we can easily predict what loss is, how much loss is coming from data structures. Thank you.